Good afternoon. We are here for AI and mathematics, which is in the mind of these two guys, is to see AI as the pocket calculator for the 21st century. It's true. And this is really a homegrown product of the computer laboratory, or Cambridge, let's say, because Alex has studied at Trinity under the supervision of Zubin Garamani, and then you spent 3 years in USA at Google, and then you came back, and now you are leading the group of AI and mathematics at DeepMind. Peter got fast here, and then the PhD in 3 years exactly, and then he started DeepMind, and now he's delaying with this fantastic book that he's doing with Michael Bronstein and Johan Bruna and Taco on the title Geometric Deep Learning, Grids, Groups, Graphs, Geodesics, and Gauges. So that you may be able, with question, to say when it's coming actually, but you can find on archive. And also I would like to mention that also another of the person who wrote this paper in Nature, who has been the basis for this talk, Mark Lackenby, is a professor of mathematics in Oxford, but he studied in Cambridge. So in some sense he's...
This meeting is being recorded.
And I will stop here.
Thank you very much for the kind introduction. So, as Pietro introduced, we'll be talking today about work over the last couple of years that myself and Peter have been doing about trying to see how AI can help mathematicians and mathematics. So the mission of DeepMind is to solve intelligence, to advance science, and benefit humanity. And in particular, the strand of work that we've been looking at is, can we advance pure mathematics? Can we advance the state of the art in pure mathematics by using the tools we have at our disposal from machine learning and artificial intelligence? And this is as distinct from many of the other interesting applications of machine learning to mathematics. For those interested in the last couple of years, we've seen really interesting advances in theorem proving, in other ways to use machine learning for automatic solutions to equations. But rather than show that machine learning can help in particular instances, what we're trying to ask here is whether or not a research pure mathematician can use these techniques to make new discoveries that mathematicians would get excited about. And this is something that at the outset we asked mathematicians what the chance of this being true was, and we got answers fairly close to zero, that machine learning was an interesting tool. It could show some things in a lot of different fields, but pure mathematics is a very specific discipline, and they couldn't see a way in which mathematics would be helped by machine learning. But as you know probably already, or can see here, we managed to have a surprising success in helping them find results that were very surprising, beautiful, and interesting to the mathematicians themselves. And so this was the cover of Nature for December last year, and highlighted on the side are some quotes from mathematicians about the results themselves, so the mathematical results, and in part the use of using machine learning to help make these discoveries. And so this was really what we were aiming for. It was whether or not we could show to mathematicians that they really should be looking seriously at machine learning if they want to make new discoveries in their field. The two fields that we chose to look into are knot theory and representation theory. And we worked very closely with some fantastic collaborators, two at Oxford, Mark Lackenby and Andras Juhasz, and one at the University of Sydney, which was Geordie Williamson, in their respective areas of mathematics. And these are the two papers that we put out alongside the Nature paper. So these are published to arXiv, and we've submitted them to mathematical journals, the respective top journals in the fields of not theory and representation theory. So we won't go too deep into the details of those papers, but we'll go through how we use machine learning to help in this process, and what that looks like at a high level, and then in particular in these examples, what does that concretely mean and what did we find? So one of the kind of inspiring phrases at the beginning of the work was looking at the kind of life and the mathematical history of Ramanujan. So Ramanujan was a famous mathematician, particularly for the kind of intuitive style of mathematics that he engaged in and is kind of remembered for. So there are stories about Ramanujan where he would be dreaming and wake up to find a new pattern that had been brought to him in his dreams by his kind of family goddess. And he would just see these patterns in numbers that other people didn't see. And it highlights one of the surprising things for me as a non-mathematician, as a kind of machine learner going into their field, that mathematics is seen by most mathematicians as a deeply intuitive endeavor, and that one of the big parts of mathematics is not just proving theorems, but also discovering new patterns, formulating these into conjectures which can then subsequently be proved. Yeah? Okay. Take that off then. So this is one way that mathematics as a discipline is practiced. This is not all of how mathematics proceeds, but some large amount of it is a kind of observational process where mathematicians care about studying particular objects, and they can generate examples of these objects, look at them to try and discern patterns which they formulate as conjectures, and then they can try and prove. So if we go back in the pre-computational era, one of the most direct examples is probably theorems about prime numbers. So in the 1800s, what they would do is they would sit down and manually calculate really large primes tables. And once they have these, you can manually inspect them and you can see patterns like the prime number theorem. And this is where those conjectures came from, which were much later subsequently proved. If we go forward in time to when computation arrived on the scene, one of the most famous conjectures in the world currently is the Birchon, Swinnerton, and Dyer conjecture, and this is one of the open Millennium Prize problems. And this was actually formulated, I believe, here at Cambridge in the 1960s, when they used the computers which were coming to Cambridge in order to calculate certain values of elliptic curves, which they could then plot, they could look at and then formulate a conjecture based on this plot. So the natural progression from this that we looked at in this work is, obviously, it's very common for mathematicians to compute examples now using reasonably large amounts of compute and computer algebra systems, but the second step of computing, computationally detecting patterns. We now have, unsurprisingly, at our disposal, tools which are very good at detecting patterns in large spaces, or looking at very large objects that might be difficult for a mathematician to even look at an individual example and start to reason about. And we'll see examples of both of these in the work that we did with mathematicians. So the process I'll describe is not a particularly automated one. This is our first foray into trying to understand the needs of mathematicians and what they can actually use machine learning for. And so this was very much a kind of iterative back and forth process between us on the machine learning side and then the mathematicians on the domain side. And it's a combination of using the pattern recognition abilities that we have with machine learning and combining that with the intuition of mathematicians who understand what avenues are going to be particularly interesting and which ones are likely to be uninteresting. So to make that slightly more precise, this is a flowchart that generally describes the process that we engage in with mathematicians from the paper. And the way we could best convey to mathematicians where this might be a useful part of the work that they do is in trying to help them discover functions that they hypothesize exist. So this process starts, if you look at the gray box to the top left, with a step where the mathematician's job is first to hypothesize the existence of a function which, if it did exist, would be interesting to the mathematician. Once we have a hypothesis of such a function, then computationally it's usually quite easy to generate some data to perform supervised learning on. So from some distribution, which we'll talk about, we're going to generate examples and observations of these examples that we wish to try and find a function for. We're going to train a supervised model to determine if such a function might exist. If we can train a supervised model at above some baseline chance, then we have increasing belief that an approximate or exact function might exist. And then secondly, what we can do is we can take our trained supervised model and we can apply attribution techniques to it to try and convey more meaningful information to the mathematician about the functions that has been learned in this case. And we can kind of look at this as an iterative loop where we can then start to answer questions, new questions of the form for a mathematician, like does a function exist? If the function does exist, can we say something about what that function is that can help them make new hypotheses and ultimately come to a conjectured candidate function which will help them prove something interesting or make a new discovery in an area that they didn't realize that patterns existed previously. So to make that more concrete, here's a very simple example that we didn't discover using machine learning, but it's the simplest one you can imagine rediscovering using a technique like this. So if we were just going to look at these recognizing patterns in these shapes, what you could do is you start with the fundamental objects that we're looking at here are the shapes, and we have measurements that we can make of said shape. So you can calculate the number of edges, faces, the number of vertices. We could look at some kind of normalized quantities of length, surface area, and volume. And we want to see if a pattern exists between these relevant measurements. So we can generate a number of examples and say a mathematician had a hypothesis that the number of faces could be predicted from the other properties of this shape. We know this is true, this is Euler's formula, but if we were going to go in this sight unseen, we could train a supervised model to predict the faces, and for any model that you choose, it should probably be able to calculate the faces exactly for the distribution that you're sampling from at the very least. Once we have a supervised model which is able to predict the faces exactly, we have a strong belief that such a function exists. We can use attribution techniques then to look at which part of the input space is responsible for predicting the number of faces. And for any good attribution technique, it should tell you that it's making this prediction based entirely on the vertices and the edges. In this simple example, once we know this information, you could plot the vertices, edges, and faces together and very easily see this linear relationship. And so the point is that machine learning isn't needed in this example because this is a simple relationship that you could see by just manually generating a bunch of examples and then plotting it and manually detecting the pattern. But we're going to see examples where this isn't the case, where we can't really do that anymore. And this is the regime where machine learning becomes interesting. This is another nice quote from Marcus de Sautoy, likening this to a telescope. I think it was a pocket calculator was mentioned before, but this is just a very narrow potential tool which really we've hopefully shown has the potential for serious impact in different areas of mathematics. So I'll quickly run through the example of knot theory first, which is a slightly simpler example, and then Petar will go into detail in the representation theory example, which is a little bit more involved. So knot theory is the study of closed loops in 3 dimensions. And so knots are very roughly what you think they are. They are kind of what we would describe in the real world as a knot, with the exception that they're closed loops. So they're kind of a single path that you can follow continuously. It's not open anywhere. And 2 knots are considered to be the same if you can smoothly deform one into another without passing it through itself. And so this is the first non-trivial knot. So a trivial knot would be an open loop, which isn't non-trivially tied or tangled together, whereas you can't smoothly deform this into a circle, which you can probably see just from looking at that rotating object. one of the things that they do in knot theory is study invariants. So these are functions of a knot that can be used to try and identify whether two knots are the same and to understand further properties about knots. So if we calculate, if we were to be given, for example, a particular, they often look at projections of knots into 2D. If we looked at a particular projection of a knot into 2D, it can be hard to tell if this is equivalent to another projection of the knot. And knot invariants are generally calculated from a diagram of the knot. And if two knots have invariants that are the same, then they are likely to be the same knot. If they have invariants that are different, then we know that they're different knots. So usually you can just think of, for the moment, knot theory is a study of these invariants. And there are lots of different invariants of knots, and some of them form different natural classes. And the two natural classes we're going to talk about are the geometry, so the geometric invariants, and what we'll call algebraic invariants. And so the geometric invariants come from this observation that knots have a unique geometry associated with them. And then you can make measurements of this geometry, like the volume and lengths of different parts of that geometry. And then there are algebraic invariants, which you can take by generating either graphs of the diagram and looking at things like its spectrum, or things that are close to its spectrum, or polynomials that are defined on the graph. And so these two different kinds of invariants come from very different branches of mathematics, and one thing which isn't really known is about direct connections between them. So we know that there is a connection between them, obviously, because they're both computable from a diagram of the knot. However, you lose information going in along either edge. And so there's not a lot known about direct connections between the geometry and the algebra. There's one particularly famous conjecture called the volume conjecture, which says that the volume is encoded by one of the invariants from the algebraic side. And that's a famous conjecture. It has a Wikipedia page, and it is as yet unsolved. So what we want to do here, first I'll just say this is an example of what a table of knot invariants would look like. So on the left, we have examples of knots, and then we have a list of geometric invariants, and on the right, a list of algebraic invariants. So this is starting to look like a pretty standard supervised learning setup. And we're just going to train, in our case, a basic MLP to predict the signature from the geometric invariants. So this is a suggestion from the mathematicians that, first of all, we're looking at this space because if such a function existed, it would be very interesting, because they didn't believe that there was one. They've been looking at this for hundreds of years and not noticed any connection directly between it, so they didn't expect one to exist, but if it did, it would be interesting. And that the signature would be a particularly relevant one to predict because of other properties about it. It's a relatively simple one, it's easy to calculate, it's also easier to prove things about. So the first surprise was that we could predict the signature very well from the geometric structure. Not perfectly, but very, very well and substantially above chance. So the second step that we take is we can just interrogate the model using attribution techniques. And so the particular attribution technique we're using here is basic gradient saliency or sensitivity. So we're looking at the sensitivity of the prediction of the model to small changes in any of the input features. And what we can see here is that clearly there are three features which are very relevant for the prediction of the signature. And you can see they all have a very similar name, and that's because they're all measurements of a similar part of the knot geometry called the cusp. So this again was very surprising, but we could communicate that the cusp seemed to be controlling the signature in some way. And after some back and forth and understanding a little bit better about what the cusp was, we together with Mark and Andras, really, proposed a new measurement of the cusp, which is called the slope, which is a simple, relatively simple transformation of those three variables that we talked about before. And we could see that the slope was in fact linearly related to the signature. And we could calculate fairly large data sets of both random knots and looking through the first million or so knots to assure that this seemed to hold. And so we came to this initial conjecture that this relationship held, that there was this linear relationship between slope and signature. with some kind of bound to do with the volume, which is based on both observation and intuition by Mark and Andras. After some amount of work, we were able to generate a counterexample to this conjecture using a certain class of knots. So this is really to make the point, when we went back, when I was saying that we were training these models, we were training them based on some distribution. So we were looking at random knots, we were looking at the first n knots. And while the conjecture held for those distributions, it didn't hold everywhere. And so we got help from the mathematicians to generate a counterexample to that particular conjecture. But then returning to the saliency, it turns out what's needed is an extra term to control this certain twisting property, which can be done either with the imaginary part of the short geodesics or the injectivity radius. So we have two refined versions of the conjecture ultimately in the paper that Mark was able to prove both cases of, where the slope and signature are linear related up to something controlled by the volume and the injectivity radius. And so this is, I believe still, yes, the first proven connection between the geometry and algebra of knots in a surprising direction that Mark and Andras did the majority of the mathematical work but wouldn't have known to follow without this investigation of machine learning. So at this point, I'll hand over to Petar to give a description of the work we subsequently did with Geordie Williamson in representation theory.
Great. Thank you very much, Alex, for covering the initial overview and some of the great results we got in the knot theory project. What I'll be telling you about was the part of our AI for Maths project which concerns a completely distinct area of pure mathematics, representation theory, and one where I have taken a more active role in leading the modeling because it involved a class of models for which I've had many years of research experience. And this was actually done in collaboration with Geordie Williamson, who was our mathematical collaborator from the University of Sydney, one of the top experts in representation theory. And besides myself and Alex, we also worked quite intensively with Charles Blundell and Lars Busing. So now, unlike the knot theory case, which could be reasonably okayish explained from the start to finish, and it was a simple kind of flat problem where we had an MLP predict a property out of a bunch of other properties. In representation theory, it is not that easy to put it together and to explain all of the backdrop within the space of a talk like this. So what I will actually do is present to you a very streamlined view of what happened along like 1.5 years of trying to make this research happen. So I only condense the part of the theory that is necessary for you to have a basic understanding of what our problem is, and also to give you a better feel for what it felt like to interact with the mathematicians while we were trying to get on the same page. When we started this project, like, make no mistakes, none of us really knew anything about representation theory, and also Geordie wasn't that familiar with machine learning, so many of our initial meetings were just lectures and deep dives designed to get us all on the same page. However, one thing that's quite encouraging, even though we tried and tested many machine learning models as we developed this theory, pretty much most of the results that we had with the machine learning models ended up impacting the final mathematical results that we've shown. So it's not that we had to like massively cherry pick what happened with our machine learning models. Pretty much every result counted in some way. So this is just to give you a feel for what those introductory sessions look like. I'm not going to dive into all of the aspects of what Geordie was able to teach us over the course of several months. But basically, there were these like massive virtual whiteboarding sessions where he would draw out these various objects that we concern ourselves in representation theory and various algorithms that we can perform over them to compute the quantities that we care about. And it was basically just a lot of this kind of stuff, like gradually, very slowly explaining to us from a perspective that we could understand how all those mathematical objects behave and what could help us cast them as objects that could be transformed by machine learning models. So this was, I think, a very important point in understanding that like a great deal of collaboration was required with a mathematician for us to be able to even attack this in any way. And also, there were a lot of very useful definitions that then ended up helping us when we had to write up the paper anyway, with various kinds of algorithmic components. So let's try to kind of distill all of that massive content of the lectures we had into kind of a streamlined story that will take us to the representation theory project and our main findings. So first of all, the main object that we will be studying here are symmetry groups. If you haven't really touched upon them in your previous work, I'll briefly say that they are just groups of transformations that transform an object in a way that doesn't change it. And one classical example of a symmetry is a permutation. You've probably encountered this when you've done any kind of combinatorics, right? You have a collection of objects, and now I perform a permutation by just changing the order of those objects. The underlying objects are still the same, I've just changed the way I've presented them. And that's the reason why permutations form a symmetry group, because they leave the underlying collection unchanged. They just modify how you see them. And they can be conveniently numerically coded like this. So here 32415 says that the first object ends up in the third position, the second object ends up in the second position, and so on and so forth. So you can assign a nice length n numerical code to every single one of these permutations. And if you've done any kind of graph representation learning or graph neural networks before this, you've probably heard quite a bit about the permutation group because they're the essence behind how graph neural networks function. Okay, now within the space of symmetry groups, we looked at a special case of symmetry group known as the Cox-Setter group. And they are special because we can describe them completely with only a subset of the transformations, which are known as reflections. Now, once again, I won't get into detail what the definition is for all of these things, but I'll just say that for the case of the permutations, the reflections are just swaps. Right? You can build up any permutation you want by just composing a bunch of swaps. This is the essence behind sorting algorithms, for example. Okay? So say you have a permutation group of 4 elements, also known as S4. You can convince yourself that there exist exactly 6 simple reflections. 6 reflections. So 6 possible swaps of 2 elements. Okay? And based on those 6 swaps, you can build the entire group just by composing them. Okay, now further digging beyond that, there's also the notion of a generator, which is a furthermore dissected set of transformations from which is even simpler, and you can use it to recover the entire group by composing. So it turns out swaps are already a too big collection, like you can reduce it. You can reduce it to just swapping adjacent elements. And once again, in sorting algorithms, you've probably seen things like insertion sort and bubble sort, which basically do any permutation you want by just swapping adjacent elements. So once again, in the case of the 4-element permutation group, 3 out of those 6 reflections are simple reflections. Swapping the first and the second element, swapping the second and the third element, and swapping the third and the fourth element. Okay, so now that we have that basic kind of hierarchy with the symmetry groups and the reflections and the simple reflections, now we can start to define what was the main problem that we wanted to solve. The key concept is that we can think about every permutation as a node in a graph, which is known as the labeled Bruhat graph. I'll get into details of that in a little bit. So permutations are nodes. Well, because it's a graph, you need to also draw edges. So how do you connect two permutations? Well, you connect them if you can recover one from the other by performing a swap. Okay, so you do one of those generators and you can recover one permutation from the other. I'll give a concrete example in a few slides' time to kind of materialize all of this. And also the graph is directed. So obviously, because if I can do a swap to go from permutation A to B, I can also do a swap to go from B to A, but we actually decide on an ordering. How do we decide it? We use the simple reflections. So we put the identity permutation, which is 1, 2, 3, 4, for the group of 4 elements, at the bottom. And then on the first level, all the permutations you can reach from it by doing an adjacent swap, and then so on and so forth. You can kind of inductively build heights of different permutations, and you do by convention that always the lower height points to the higher height when you draw an edge. Okay? So this now gives you a directed graph where the permutations are nodes. And this is an example of a labeled Bruhat graph for the permutation group S4. So you can see at the bottom we have the identity permutation 1, 2, 3, 4. It is connected to these 3 permutations by performing the adjacent swaps. It's also connected to some permutations further up, but they're not caused by simple swaps. They're caused by a more complicated swap. So that's why those lines are dashed. They're not immediate neighbors in this overall graph. Okay? So this is the object that we are working with in the particular case of representation theory. As you can imagine, because we're working with graphs, probably there will be a graph neural network at some point, but let's wait a little bit more before we mention that. Okay, and now we can define what is the conjecture that we care about attacking in this particular case. What we do is start by taking any two elements of this group, so any two permutations, and based on them you can define two objects. The first object, called the Bruhat interval, is a subgraph of that previous graph I showed you, which contains all the paths between those two permutations, and fundamentally it is unlabeled. You drop all of that nice labeling information you had before. You don't know which node corresponds to which permutation, you don't know which edge corresponds to which swap, all of that is erased. You just have a subgraph containing all paths between two permutations. That's it. Like you have its shape. You don't have anything else. And the second thing you can compute from these two objects is the so-called Kazhdan-Lushtik or KL polynomial, which I won't get into the details of how it's constructed, but it's basically a polynomial with integer coefficients. And it's a long-standing conjecture in representation theory, one of the main conjectures in representation theory by Lushtik and Dyer, that these two objects are fundamentally related, that you can compute the coefficients of the polynomial from that unlabeled subgraph. And this is known as the combinatorial invariance conjecture, which has stood virtually unattacked for 50 years. And I'll explain in a bit why exactly, well, a possible reason for why it wasn't attacked for so long. But generally, this is the task that we're after, right? We have some of these subgraphs corresponding to various permutation paths, and we have to, based on that graph, predict coefficients of a polynomial, okay? And we know those coefficients are integers. Now, the reason why this was so tricky for mathematicians to attack, even if they're like experts in the area, is because usually this polynomial that you have to predict is really, really, really simple, okay? So in most cases, it will be 1q or 1 plus q, very simple example, right? So this here is, I think, the only non-trivial example in the group of 4 elements, the so-called crown graph, which here I've just drawn the labels for convenience, but in principle you don't get to see what permutation is in every node. And the polynomial for that one is the 1 plus q, and that's the only polynomial that has a q in the group of 4 elements, okay? Now, obviously, because these are polynomials, you would expect q squared to appear at some point. Well, the smallest example where q squared appears is this one, okay? Like, this is one of the simplest examples and just about manages to get you a coefficient of q squared in there. Obviously, as you make them more and more complicated, q cubed will appear, q to the 4th, and so on. But the problem is already at this point, I hope you can agree with me, it is really, really, really tricky to make sense of what the hell is going on in this graph, right? And it was definitely the case for mathematicians who had to work with these objects as well. You could visualize them, but can you easily make sense of what are the patterns that are going on here? It's just a lot of information to process at once. And that's probably the reason why this problem stood unattacked for such a long time. And just to kind of give you a feel, obviously what we want to do now is to use machine learning, just like Alex explained, to try to predict the coefficients from the graph. And this is just an example for what kind of training data we give to the model, right? So here is one of those graphs. As I said, I had to strip away all the information about what are the permutations, what are the types of edges, so on. I just have a bare stripped graph like this. And I have a coefficients of the polynomial at the output level that I want to predict. And it can also get a little bit more complicated if you want to get a little bit more targets. But here, once again, this is one of the easier examples where you can get all of these coefficients at the same time. So very tricky for humans to analyze what's going on here. But maybe machine learning will have a better chance of doing this. Now, the big question arises before we try to do machine learning on this is what's the model? What's the machine learning technique that we should use? And in order to better understand what would be a good machine learning model, all of those lectures we did together with our math collaborator came really in handy, because when I give you all of that privileged information, like when I tell you which node is which permutation, which edge is which swap, there actually exist algorithms that will compute the polynomial perfectly, okay? And Jordi explained to us what were the algorithms used to compute those polynomials from the labeled graph. And it turns out this is the main equation that's being performed here. So the polynomial stored in a particular node of the graph is equal to some summation over some other polynomial stored in the graph, and then followed by some function that chops off all negative powers in the polynomial, okay? So for those of you who might have seen some graph neural network stuff before, this feels a lot like a one-hop graph neural network with the sum aggregation. So you're kind of doing the sum over all of your neighbor features in the graph. And this function, which chops off negative stuff, just sets it to 0, is very similar to the standard ReLU activation, which is used across machine learning as like a standard activation function that just sets everything negative to 0, right? So we hypothesized based on this, that it would be very useful to use graph neural networks with the sum aggregation and the ReLU activation. And we use this exactly as the model to fit the polynomial coefficients. And to be very specific, the task that we look at is graph classification. So based on the input graph structure, we try to classify this graph into the coefficient that corresponds to 0, 1, 2, 3, and largest value in our data set. And the hypothesis that we did by doing this is that because these algorithms work perfectly well when you have all that privileged information, the hope is that the graph neural network might be able to recover that privileged information from the graph structure and then kind of run the algorithm internally, okay? That's the reason why we primed it to perform in this particular way. And okay, we built a data set of all the graphs that we could find of interest in intervals up to the permutation group of 9 elements. That's already 9 factorial, so that's quite big. And we trained the GNN to predict the various coefficients of q, q squared, q cubed, q to the 4. And here you can see the majority class at the top and the performance of our first GNN model. And already you can see something that is quite potentially exciting, because the graph neural network learned to predict it substantially better than the majority classifier, meaning it has detected some pattern. There exists something in there. And already this was quite encouraging, as Alex already mentioned in the case of knots. Already seeing a number go up like this can be quite encouraging for the mathematician, because their intuition that something exists there can be validated by seeing a number like this. So this was already quite encouraging, because previously, like before we did this work, there existed some algorithm for computing the coefficient of q and nothing else. We didn't really know anything else about these graphs. So naturally, we wanted to interrogate this GNN and ask it, okay, what did you learn to do? Where did this pattern come from? And what we did is we used a similar kind of gradient saliency method like we used in the knots theory project, but now accounting for the fact that our input is a graph, to actually pick out some particular nodes and edges that were deemed most important by the graph neural network for making its prediction, and then sending those graphs to our math collaborator, because we couldn't really make sense of what was going on in these graphs, but hopefully maybe our collaborator would be able to spot something in there, because now these graphs, these detected subgraphs, are much smaller than the original huge graph that we had to deal with. So maybe now it will be a bit easier to spot what's going on. And it turns out that after staring at these graphs for about 2 weeks or so, I believe our collaborator was able to figure out that there is some very interesting piece of related work on diamond completion. A diamond is just this kind of graph with 4 edges that closes itself. That seemed quite relevant to the patterns that our model was picking up on. And therefore, he proposed that we try to extract all of these substructures, these neighbors and diamonds, and serve them as direct features to the graph neural network to see if that would improve the performance, like to validate whether these substructures are really that useful for the polynomial coefficients. So we trained the GNN again, this time adding the extra features corresponding to those substructures extracted at the beginning. And, well, I don't know, this looks pretty good, right? I hope you would agree this looks pretty good. It looks much better than before, right? So this gave us a pretty encouraging result that we were onto something, and we actually detected a pattern that would prove critical for deriving a more deep connection between the graph structure and the polynomial, therefore hopefully settling the conjecture. Now, to actually make a very concrete advancement, we needed to make one more observation, which also relied on these visualizations that we showed to Jordi before, and that is Obviously, when we're analyzing what the graph net learned to focus on, we can reintroduce privileged information, right? We can see which permutations were more favored, which edges were more favored. And we did a simple thing. We plotted a heat map of what kinds of swaps, because remember, every edge corresponds to a swap, which swaps were more favored by the model when deciding the coefficient. And it turned out that the model really favored extremal swaps, so swaps that swap element 0 or element 8, like the elements at the ends of the array. And this turned out to be a very critical observation. In fact, one of our reviewers on the Nature paper said that this observation is something they would have only expected from a handful of great experts in representation theory, and, quote, "it is such a human suggestion that it gave them goosebumps." And using this extra observation about the extremal swaps combined with the representations that we discovered before, Jordi was able to detect this hypercube decomposition, which splits the input graph into two parts, an inductive piece that you can do induction over, and a piece that has a shape like a hypercube. And he was actually then able to prove a theorem that for every graph that I give you, there exists one decomposition like this, a canonical hypercube decomposition, from which you can directly compute the polynomial. Okay, so this almost feels like we have settled the conjecture, but the problem with this theorem that we've been able to prove is that we showed there exists one. We haven't told you how to compute it, right? So just the fact that it exists doesn't mean that it's possible to find it using some computational methods. However, we then, other than just trying to prove how to find it, we also tried just to do the good old-fashioned brute force approach. Let's try all possible hypercube decompositions and see how often they fail to predict the polynomial. Well, on basically every interval we've been able to test so far, any hypercube decomposition has worked up to S8 and S9. So, guided by this, we made a conjecture that no matter what hypercube decomposition you find, and you can find an arbitrary one without a lot of problem, you should still be able to use Jordi's formula to compute the polynomial. Now, this is something we still haven't proven, and it's now out there for mathematicians to try to prove. But if we were able to prove this, we would settle the combinatorial invariance conjecture, which would be a pretty massive result, given that this stood virtually unattacked for 50 years, and it's one of the central problems of all representation theory. So by using machine learning, we've been able to first prove a very important result that discovers new important substructures in the area, but then also conjecture a new approach that could usher in a whole new family of approaches for attacking this problem, which previously the graphs were just too big to make proper sense of them. And that was actually our last slide. Thank you so much for listening. We'd be very happy to take some questions if you have. And if you want to talk to us offline, our email addresses are listed on this slide. Thank you to all our collaborators once again. Thank you so much. So I believe we can take some questions from the audience. Pietro, if you see some questions on Zoom, we can also answer those.
Yes, but what I would like to say for the people who are on Zoom, the recording will be optimal, so that they will, if anybody has got problems in listening, that will be something that will be completely good in the version that we will post.
Yeah. Okay, so are there any questions? Yes.
I was wondering, what is, like, it looks from your results that most of the feedback you can provide to mathematicians is related to how well you can explain a deep neural network. Like, as you've shown from the last few slides, just by showing a graph, the explanation of what the GNN has learned has led to this advance. So I was wondering, what's your opinion in tasks where explanations can be more complex? What's the relationship with discoveries and explainability?
So I have a pretty harsh opinion on this, which is basically our current explainability techniques are rather terrible. And the fact that Jordi, who's one of the top 5 experts in this field in the world right now, was able to see something in there, we got pretty lucky. But the fact that we got pretty lucky doesn't mean that we should settle for the status quo. We should actually use this as a drive to improve our explainability techniques, just exactly so that when we try to tackle more challenging problems. Alex, do you have some thoughts on this too?
Yeah, I think you captured that pretty well. I think this is one of the best demonstrations of a project where we really care about explainability and it makes a big difference. I think there's some point that Petter made well during the second half that sometimes for a mathematician, just knowing that a path has promise and that it's worth them sitting down for a week to really attack it is very valuable to them. But really the breakthrough in the representation theory was about making this connection with explainability, and we did get lucky. I think as a machine learning community, we should be able to do better.
Yes?
Yes, in the first project, after you found out there was a correlation, how did you come up with the formula, like kind of the slope idea? Is it just brute force or intuition, or can the neural network do anything in there?
Yeah, that's a great question. I'll kind of field the knot theory side. So in this case, it was come up with by our collaborators. So just by virtue of showing them that the cusp was the relevant measurement and then showing them a couple of plots, that's a sufficiently constrained domain that they could use their intuition to say, well, what kind of measurements could possibly be relevant here? And this was one of the ones that they came up with relatively quickly. But I think you make a good point that especially in that case, it's a relatively simple formula. Using other techniques, we probably could have got there without making them do that side of the work.
So what motivated you to choose these two problems? Have you thought that you have a good shot solving at these two problems?
Well, these were the first two places that we tried. Is certainly one motivation. So we had obviously access to some pretty fantastic collaborators in both areas. But I think it is a point worth making that we tried first looking in knot theory because it seems like topology, low-dimensional topology, is a fairly computational area. It could provide some interesting patterns to look for. And then representation theory was the next one that we looked at, and we were able to find something there as well in a completely distinct area of maths, which I think gives us hope that this really does generalize across all of mathematicians' work rather than being constrained to a particular area.
Yes?
Thank you for the wonderful talk. It's a fascinating connection. I was very excited when I saw this paper. So I have a two-fold question. So first question is, what are some of the directions you're looking to explore moving forward? And second is a more specific question about the kind of mathematical things one could conceive machine learning being able to help with, which has to do with number theoretical data sets. So because mathematical data which replicates on computation will have a lot of structure, it might be possible to build simple ML models very easily, which are also highly generalizable. But this effect does not seem to happen in many number theoretic examples. Take, for example, the Bruhat function, which counts the number of prime factors. And because analytic forms are not known for some of these functions, how would one proceed in terms of machine learning dealing with some number theoretic data sets?
I think that's a great question. Would you want to field this one, Petter?
I think you're better fits to answer.
Okay. If you want to jump in maybe about like structure for networks and that kind of thing, I think maybe that's a kind of general point that you might be interested in. But yes, on the second question on number theory, I think number theory is certainly an area that has the most functions that might be surprising if you could learn them, if that makes sense. They have properties which make them not efficiently learnable by machine learning, potentially not. However, I think there are also areas in number theory which are just quite mysterious and could really benefit from this technique. So I would be fairly bullish that we'll be able to find some interesting connections in number theory, but one of the constraining factors, honestly, in this work is actually us and collaborating together because it took a while to get a sufficient working understanding of knot theory. As Petter mentioned, representation theory was a little bit harder, but even these objects are quite simple compared to some of the more sophisticated areas of number theory. And so in order to get a good run at this, I think you might expect you'd need someone who has a reasonable background in both number theory and machine learning to identify places where you could reasonably expect to learn a function. And I think that there was another question embedded there. What was the first one?
What are the areas we want to explore in the future?
All of maths.
Yes.
So I guess the long-term aim, right, is to eliminate you go
I think. Yeah, I can take this one. Thank you very much. That's a very important question. I would say that yes, that is definitely our aim. We want to empower the mathematicians to just use tools like this by themselves. They've already been able to do so on some simple cases like combinatorics. There have been some really cool papers from Adam Zolt-Wagner recently in disproving some conjectures in graph theory. But I think the main obstacle to making a general pocket calculator is that every mathematical object comes with its own domain and its own set of symmetries, which means you need to build a custom machine learning model for that domain respecting those symmetries. So in knot theory, we could get away with a simple flat neural network. For representation theory, I had to devise this, complicated graph neural network that respected the mathematics behind it, right? So the real problem to address will be generality and how do we properly empower mathematicians to use it. I feel like geometric deep learning, which I'm currently advocating for, is one direction that could really help there because it's kind of a blueprint for cooking up your own neural network depending on the objects you have. And maybe it could be more accessible to explain it to mathematicians. But yeah, it's anybody's guess at this point. The main hindering fact is that every domain comes with its own symmetries. Yeah. I think we have time maybe for one more question. Yes? Do you have some thoughts on this?
And Petar might also have his own answer to this question. But I would say that I would consider a really great outcome from this work is convincing mathematicians that it's a good idea to collaborate with people in machine learning and vice versa, because this was together several years of working very closely with mathematicians in order to get these results. And so I think the only way that this scales is an increasing light in the mathematical community that machine learning is valuable for them and wanting to reach out to people in machine learning, and for people in machine learning seeing that we can take these techniques and get these kind of results. And so I think naturally, if people are interested in it and they see the value in this, then this will go to whichever part of mathematics is actually going to get value from it.
I'd like to just double down on what Alex just said to say that what we really want, as we said, is not a machine learning system to replace a mathematician. We want a machine learning system that any mathematician can use, which is a very different thing. So we want to get it to a point where, like as Alex said at the beginning, when we started this project, we asked a bunch of mathematicians, do you think this would be potentially useful? And they said no. Most of them said no. And now we've been able to actually convince quite a few of them that maybe there is something there. So the hope is gradually to convince more and more people that this technique could be applicable in their area, and then we can basically rely on them to drive the progress in their respective field, like a more distributed system rather than a centralized thing that everybody uses. Yeah.